Okay, today we are doing an activity. The aim of this activity is to enable you to describe a topic to someone else, because in the exam, what I found is that the main problem is you put the keywords in, but it's not understandable from the paper. So it is important that when I read the paper, I should understand the topic and I should understand it the way I taught in the class. And also, the other parameter of this is if there is a junior student, like a first year or second year student, if he or she reads your papers, they should be understanding the topic as well. So whenever I give a question, when I read the answer, it should be compact, not too long, not too short, not only involving keywords, but someone who's reading it should understand the concept fully. That's why we are doing this activity today, because you have the question set and you have the answer set, but you will again try to convey the information with your own words and with your own animations. And another important thing, your videos should be less than 5 minutes in the end after editing. So you should do some editing. In the end, it should be less than 5 minutes. Okay. Today, we are doing the videos today. Then I will add the videos to this, my introduction, and I will upload it onto YouTube. So if you do not want to be seen on YouTube, then you can just record the screenshots, or just you can record the your drawings. Or if you want to be seen, if you have no problem, then you can come to the board and use the board to tell the subject as well. Okay, then we can start.
Many enzymes need small molecules called cofactors to be catalytically active. When an enzyme lacks its cofactor, it's called an apoenzyme, which by itself is inactive. Once the apoenzyme binds to its required cofactor, it becomes a holoenzyme, which is the fully functional catalytically active form. These cofactors can either be metal ions, such as zinc or magnesium, or organic molecules known as coenzymes, which are often derived from vitamins. So, apoenzymes and cofactors create enzymes speed up both the forward and reverse reactions by lowering the activation energy, also called the Gibbs free energy of activation. They promote the formation of the transition state, which is the high energy intermediate between substrate and product. Importantly, enzymes do not change the equilibrium position and do not alter the overall free energy change of reaction. So among the options, the true ones are the activation energy is lowered, transition state formation is promoted, and rate constants for both directions increased. The equilibrium itself stays the same. So enzymes just help. During a chemical reaction, the substrate first passes through a transition state, which requires energy input. This is the activation energy. However, once the transition state forms and collapses into the product, that energy is released back. Therefore, activation energy does not affect the net free energy change between reactants and products. Delta G only depends on the free energy difference between the initial reactants and final products, not the path taken or how fast the reaction occurs. So, while the activation energy determines rates, delta G determines.
First question asks which of these reactions is antagonic and which one is hexagonic. In the first reaction, the substrate energy is higher than the product, so the substrate are less stable, and the free energy is lower than zero, so the delta G is zero, and therefore this reaction is hexagonic. In the second reaction, the substrate traits energy is lower than the products, so the substrates are more stable and the products are less stable, and the free energy is greater than zero, so the reaction is antagonic. In question 5, it asks what is the equilibrium for the reaction, what is the delta G, and in part B, it asks suppose an enzyme enhances the ratio of the reaction by 100-fold. What are the rate constants for the enzyme catalyzed reactions, and what is the equilibrium constant delta G? To solve for delta G, we have to first find the K value, which is K forward over K reverse. K forward is 10 to the minus 4 and K reverse is 10 to the minus 6, and therefore the K value is 100. For finding the delta G, we have to solve this equation, and when the equation is solved, the value is minus 11 to the minus 11.42 kilojoule per moles, and this is the delta G value. And when we increase the enhances rate by 100, the K forward is 10 to the minus 2 and K reverse is 10 to the minus 4, which again gives a K value of 100, so the delta G will not change. In question 6, the question asks what would be the result of an enzyme having a greater binding energy for the substrate than for the transition state. First, we have to know what is the transition state. The transition state is a transitory molecular structure that is no longer the substrate but is not yet the product. Enzymes accelerate reactions by facilitating the formation of the transition state. If an enzyme had a greater binding energy for the substrate than for the transition state, the energy substrate complex would be more stable than the enzyme transition state complex. As a result, the transition state would not form and catalysis would not take place. Enzymes accelerate the rate of both the forward and the reverse reactions. Enzymes do not affect the thermodynamics and therefore do not alter reaction equilibria, rather they increase the rate at which equilibrium is attained.
In our question, we are asked to match the K equilibrium values with the appropriate delta G values. But before solving the question, let's look at some general information. Delta G, or Gibbs free energy change, determines the reaction spontaneity. If this energy is calculated as negative, the reaction is spontaneous, and if it is positive, the reaction is non-spontaneous. And we measure this free energy under standard conditions, which means we take 1 molar of reactants and products, we set the environment in 298 Kelvin, which is 25 degree or room temperature, and we take the pH equal to 7. And we can calculate this energy with this formula. However, in our question, we are calculating the free energy under standard conditions. We have 1 molar of reactants and 1 molar of products, which means our reaction is in equilibrium condition, which makes the delta G 0. Therefore, we can arrange this equation in this. And our R value is equal to 8.215 times 10 to the minus 3 kilojoule per mole times Kelvin, and our temperature is equal to 298 Kelvin. Therefore, our calculations are like this.
So in this question, we have a reaction from glycolysis, and we are asked for the equilibrium constant and Gibbs free energy. First of all, we should look at the concentration of the compounds, and we see that G6P actually has a higher concentration than G1P in equilibrium, which means that the reaction is favored towards G6P, and we can take it as a product while we take G1P as the reactant. Here is our formula for equilibrium constant. We divide the concentration of product by the concentration of reactant, which is 0.0 19 molars over 0.01 molars, which is 19, and there's no unit since the molars are cancelled. Then we come to this equation to find our Gibbs free energy. In equilibrium, this G equals 0, and we have to find the standard free Gibbs energy. The formula here is turned into this. If we take G as 0, we plug in the value of equilibrium constant as 19, and since I did the calculations beforehand, we get this negative 7.3 kilojoules per mole. That would mean our reaction is exogenous and spontaneous when G1P is turned into G6P.
So for this question, we are given a solution of 0.1 molars concentration of glucose 6-phosphate or G6P, and in the solution, enzyme phosphoglucomatase is added. And this produces the following reaction where G6P is converted into G1P. The question also gives us the Gibbs free energy and asks us to find the final concentrations and the cellular conditions under which G1P produced at a high rate. For the first part of the question, we're going to be using the Gibbs free energy equation to calculate the equilibrium constant. This is the equation where R is the gas constant, T is the temperature in kelvins, this is Gibbs free energy, and the equilibrium constant. As we know, equilibrium constant equals this, the ratio of concentration of G1P over G6P. So we're gonna put it in here and then solve by putting in all the numbers. This is the solving part, and we get this equation, but because the ratio is less than 1, it's better to use its reciprocal. So we get this equation, which means that 1 molecule of G1P is needed for every 21 molecules of G6P. So then we're going to be calculating the final concentrations with starting concentration of 0.1. When we calculate that, we get this final concentration for G1P and this final concentration for G6P. For the second part of the equation of the question, we can say that equilibrium constant less than 1 favors the reactant G6P, and therefore the reaction does not proceed as written in here. So for high G1P production, we're going to need to supply G6P at a high rate or remove G1P at a high rate, because the equation favors this part.
Okay, so for question 11, let's quickly go over the 3 main types of enzyme inhibition. So first, we have the competitive inhibition. Here, the inhibitor looks like the substrate and competes for the active site. That means the substrate cannot bind when the inhibitor is there. So Vmax stays the same, but Km increases because you need more substrate to reach half max speed. For example, we can think about sulfanilamide or anything that blocks the active site. Second, we have the uncompetitive inhibition. The inhibitor only binds to the enzyme substrate complex, never to the free enzyme. It's really important. It lowers both Vmax and Km because it traps the enzyme once the substrate is already bound. And finally, we have non-competitive inhibition. So here the inhibitor can bind whether or not the substrate is attached. That means Km stays the same, but Vmax drops since the enzyme's overall activity is reduced. We can think about Roundup and doxycycline for an example for this. So lastly, it's really important to remember the competitive fights for the active site, and the uncompetitive waits for the complex, and the non-competitive ones, they shut down the whole thing. And that's the whole question.
This is our question. This is solved by Michaelis-Merten equation, step by step. For initial rates, we did this calculation. Both sides are divided by Vmax to get fraction of Vmax. The substrate concentration is equal to 10 km according to the question. We plug in that value and we find out that the fraction is approximately 0.9. From this fraction we can say that the
V0 equals to 0.9 Vmax, and this means that 90% of Vmax equals to V0. Now we plugged in the substrate concentration to 20 km according to the question. After the plugging in, the fraction equal to 0.95, and that means that V0 is approximately equal to 0.952 Vmax. And we can infer that the percentage is 95.24%. The interpretation we can make out of this is increasing substrate concentration beyond km gets you closer to Vmax, but with diminishing returns, each doubling of substrate concentration adds less to the fraction.
Okay, so we are going to talk about enzymes and substrates, and let's start with the basics. So in this complex reaction, E is the enzyme and S is the substrate, and ES is the temporary complex that is formed. And it can either break apart again or go to make another product called P. And here, as we can see, there are some different kinds of constants. And these constants are K1 is the dissociation rate constant, where ES dissociates into E to S. And K1 is the association rate constant, where ES forms to make the temporary complex ES. And K2 is the association rate constant that after it further completes the reaction, it forms the new product P. And we have the Michaelis constant, which is written as Km, and it tells us the substrate concentration where the reaction rate is half of its maximum. And mathematically it can be written as K1 plus K2 divided by K1. And also, we have a dissociation rate constant, which is Kv, and it tells us how tightly the enzyme and substrate stick together. And it can be written as K/1 divided by K1. And so Km is not the same as Ka because Km also includes K2. This is the step where product is made. And that means Km does not only measure how strong the binding is, it also depends on how fast the product forms. But if the enzyme is slow at making product, meaning K2 is much smaller than K1, then the K2 term does not really matter. But in this case, the Km and Kd are not equal to one another, and that means the only way that Km and Kd are equal to one another is where Kd is much more smaller than K1, and the effect of Kd is K2 is negligible. So as a result, a large Km means weak binding, and you need lots of substrate to reach half max speed, and a small Km means strong binding, and we need the enzyme holds on to the substrate easily. And that's it.
What is the defining characteristic for an enzyme catalyzing a sequential reaction and a double displacement reaction? In a sequential reaction, all substrates must bind to the enzyme before any product is released, as can be seen, forming a ternary complex. It can be ordered or random, depending on whether the binding order matters. In a double displacement reaction, or a ping-pong reaction, one substrate binds first, reacts with the enzyme to form a temporary modified enzyme, and the first product is released before the second substrate binds. We have isolated two versions of the same enzyme, a wild type and a mutant, differing from the wild type as a single amino acid. Working carefully but expeditiously, you then establish the following kinetic characteristics of the enzymes. With the assumption that the reaction occurs in two steps, in which K1 is much larger than K2, which enzyme has the higher affinity for substrates? So we know that enzyme substrate affinity is inversely proportional to Km values. And here in the table, when we look at the Km values, we see that mutant Km value is lower, which indicates a higher substrate affinity. So we can say that the mutant enzyme binds the substrate more tightly. Now let's look at the B part. What is the initial velocity of the reaction catalyzed by the wild type enzyme when the substrate concentration is 10? Here we use Michaelis-Menten equation, as can be seen here. We have to plug in the values for the wild type. For Vmax, we write 100, and our concentration is given, it's 10 millimolars. And we also write the Km values. And from the equation, we get 50 moles per minute. So the initial velocity is 50 micromoles per minute. And now the last part, which enzyme alters the equilibrium more in the direction of product? So we know for a fact that enzymes do not change equilibrium. They only speed up the rate of reaching equilibrium. And even though the mutant has a higher affinity and lower Vmax, the position of equilibrium remains the same because free energy change is not affected by the enzymes. So neither enzyme changes the equilibrium position. Enzymes affect reaction rates, not equilibrium.
Hello everyone. Today we are going to solve the 19th question of the chapter 5 questions. In this question, we see three different Lineweaver-Burke plots for the enzyme activations. In order to solve this problem, we use Michaelis-Menten kinetics. This is a model of enzyme kinetics that explains how the rate or velocity of an enzyme catalyzed reaction depends on enzyme and substrate concentrations. The Vmax is the maximum speed of the reaction that changes depending on the enzyme's concentration. The Km is enzyme's efficiency. Vmax is the y-intercept on Lineweaver-Burke plot and Km is the x-intercept. For this question, we can see that we only use one enzyme type and change its concentration only. So, the x-intercept, which is the Km, should all be the same for each of the curve. But as the enzyme concentration increases, its maximum speed of reaction should increase too. Based on this information, our answer should be the B graph, as its x-intercept is all the same and its y-intercept changes depending on the enzyme concentration.
The graph illustrates the standard Michaelis-Menten kinetics, which plots the initial reaction speed against the concentration of substrate. The curve shows that the reaction velocity asymptotically approaches the maximum velocity. The Michaelis constant is defined as the substrate concentration required to reach the half of the maximum velocity. A lower Km indicates a higher affinity of the enzyme for its substrate.
The two enzymes, asparaginase 1 and asparaginase 2, are compared. Asparaginase 1 has higher Vmax, meaning it can catalyze the reaction faster overall. Asparaginase 2 has a lower Km. It has a higher affinity for the substrate.
In conclusion, asparaginase 2 is the more effective chemotherapeutic agent. This because at low substrate concentrations typically found in the body, the enzyme with the higher affinity will exhibit greater activity, making it better depleting the necessary substrate, which is asparagine, for therapeutic effect, even though its ultimate maximal speed is lower.
21st question, it says, picture in your mind the velocity versus substrate concentration curve for a typical Michaelis-Menten enzyme. Now imagine that the experimental conditions are altered as described below. For each of the conditions described, fill in the table indicating precisely the effect of Vmax and Km of the imagined Michaelis-Menten enzyme. First, it asks in the A and B what happens when the enzyme concentration is changed. So in a basic Michaelis-Menten reaction, first we have the enzyme and substrate, which then turns into enzyme-substrate complex, and then returns into enzyme and product. We know that we reach maximum velocity when all enzymes are bound to the substrate, which is denoted here as Vmax equal to K multiplied with total enzyme concentration. So we would know that if the enzyme concentration is twice as much, enzyme is twice as much, then the velocity would be doubled, and if the enzyme is half as much, the velocity would be twice as much reduced. And the Michelin constant Km represents the substrate concentration at which the reaction rate is half of Vmax. It shows the enzyme's affinity for the substrate, and low Km shows that the enzyme binds substrate more tightly, and high Km shows that the enzyme binds substrate weakly. So the Km is independent of the enzyme concentration, so in A and B the Km wouldn't change, and in A the Vmax would double, and in B the Vmax would halve.
In the option C, a competitive inhibitor is present. The inhibitor competes with the substrate for the active site. Adding more substrate can overcome it, so the max rate stays the same. No change. But you need more substrate to reach half max speed, so Km increases. Option D, an uncompetitive inhibitor is present. This inhibitor only binds to the enzyme substrate complex, forming an inactive ESI complex that reduces the overall reaction rate, so Vmax drops. Because it traps ES, the enzyme appears to have higher substrate affinity, so Km decreases. In option E, a pure non-competitive inhibitor is present. It binds to a different site on the enzyme, not the active site, and inactivates enzymes whether or not substrate is present. With fewer active enzymes, Vmax falls, and binding of substrate isn't affected, so Km stays the same. No change.
I'll be doing the question 22. It says in the conversion of A into D in the following biochemical pathway, enzymes EA, EB, and EC have the Km values indicated under each enzyme. If all of the substrates and products are present at a concentration of A minus 4 molar, and the enzymes have approximately the same Vmax, which step will be the rate limiting and why? And we'll look at the steps one by one. First, we'll look for enzyme AB. The Km is 10 to the negative 4, and the substrate concentration is also 10 to the minus 4 molar. That means enzyme AB is working at half of its maximal velocity, so it's Vmax divided by 2. We know this because Km is the substrate concentration at which the reaction rate is half maximal. So as the two of them are equal, we would know that it's Vmax divided by 2. So now we'll look at AC. The substrate concentration is again 10 to the minus 4 molar, and it's 100 times greater than its Km value, which is 10 to the minus 6. So we would know that the enzyme is almost fully saturated, and AC operates very close to Vmax. So we would say that this is Vmax. And then we'll look at EA. The substrate concentration is 10 to the minus 4, and it's 100 times lower than Km, which is 10 to the minus 2. So the rate is much lower than Vmax, approximately, like the enzyme is operating only about 1%. So in conclusion, we would say that EA is the slowest because its substrate concentration is much smaller than its Km. So it only works at about 1% of its maximum rate. So the limiting step is EA.
Proteins are thermodynamically unstable. The delta G of the hydrolysis of proteins is quite negative, yet proteins can be quite stable. The delta G negative of proteins are kinetically stable because the rate of hydrolysis is extremely slow without enzymes. The peptide bond has a high activation energy barrier, so spontaneous breakdown does not occur readily. This is a reaction energy diagram that shows the relationship between the free energy and the progress of the reaction. On the y-axis, we have free energy and how much energy the molecules contain. On the x-axis, we have a reaction progress showing that the change from protein to amino acid. The proteins start at a higher level energy and the amino acids are at a lower energy level, meaning that the negative of delta G, so the reaction hydrolysis, is thermodynamically favorable. However, there is a large energy barrier between them. This is the activation energy. It represents the energy required for the reaction to start. Because this barrier is high, the reaction is very slow, unless an enzyme catalyzes it.
Transition state analogs, which can be used as enzyme inhibitors and to generate catalytic antibodies, are often difficult to synthesize, such as the reason. For answer this question, our answer is transition states exist on different extremely short time and are high energy and stable structures. Designing stable molecules that closely mimic this fleeting high energy state is very difficult. Moreover, the exact geometry and electronic structure of the transition state are often theoretical or uncertain, making chemical synthesis of accurate analogs challenging. So, for conclusion, transition state analogs are hard to synthesize because they must resemble an unstable, high energy configuration while still being chemically stable enough to isolate.
What is the biochemical advantage of having a Km approximately equal to the substrate concentration normally available to an enzyme? When the substrate concentration is approximately equal to the enzyme Km, enzyme operates at about half of its maximum velocity. This condition provides a major biochemical advantage because the enzyme's reaction rate becomes highly sensitive to small changes in substrate concentration. As a result, the enzyme can efficiently adjust its activity in response to fluctuations in substrate levels inside the cell. This allows for fine regulation of metabolic pathways, ensuring that the enzyme is neither working at full capacity unnecessarily nor inactive when substrate levels change. Thus, having a Km equal to the S substrate enables flexible and energy-efficient control of enzyme activity, maintaining metabolic balance in the cell.
Hello everyone, we are group 10 from Biochemistry and today we are going to explain this question. The question is that acetylcholine is a fast-acting, short-duration muscle relaxant. It's often used during anesthesia, especially before inserting a breathing tube. And it works as a competitive inhibitor of acetylcholinesterase, the enzyme that normally breaks down acetylcholine at neuromuscular junctions. Because acetylcholinesterase is inhibited, acetylcholine can't act properly and muscle paralysis occurs. The drug is then broken down by serum cholinesterase, which is found in blood plasma. Once acetylcholine is hydrolyzed, normal muscle function returns, typically within a few minutes. The first question is that why is measuring serum cholinesterase activity before the procedure a good idea? Because some people have low enzyme activity. Because some people have low enzyme activity or a mutant form of serum cholinesterase. Measuring serum cholinesterase beforehand helps identify patients with abnormally low or defective enzyme activity. This prevents unexpected prolonged paralysis and ensures that procedure can be done safely. The second question is, what happens if the enzyme activity is only 10 units liters instead of the normal 80 units liters? If the enzyme activity is much lower, acetylcholine will be hydrolyzed very slowly. That means pyrolysis will last far longer, which possibly hours instead of minutes. With only 10 units liters activity, the breakdown of acetylcholine would be greatly delayed, causing prolonged inability to breathe and extended muscle paralysis. The last question is, what if the mutant enzyme has a What if the mutant enzyme has a Km of 10 mm instead of 1.4 micromolars? Km measures how strongly an enzyme binds its substrate. Higher Km, lower affinity. It means that the mutant enzyme would have a much lower affinity for acetylcholine. The drug would be metabolized more slowly, leading to prolonged paralysis and respiratory arrest risk after administration. This was the last question. Thank you all for listening.